Good morning, students, and welcome to the today's session. Today, we are going to start with the last unit that is about measurement of various kinds of parameters. In this unit, we will be talking about measurement of temperature, speed, vibrations, frequency, voltage, etc. How with using different devices we can actually use these various, we can measure these various parameters. So in today's session, we are going to talk about the measurement of temperature. Some of the things you must already be knowing also. Some of the devices that are very commonly known to all of us. So we'll be just giving it a quick review, and we'll be talking of different methods with the help of which we can actually measure temperature. So based upon the nature of the change produced, we can actually have certain classifications for the temperature measuring devices. The first one is glass thermometer. This is the most popularly used phenomena. The normal home thermometers that you use, mercury thermometers, which are actually based on the principle of expansion of liquid. Like you all must have seen the thermometers that you all have in your homes. They are based on this. So when the bulb it gets heated up, when you subject it to a rise in temperature, basically the mercury that is filled in a glass tube, it expands with that heat, it rises in that glass column and it indicates the change in temperature. So that is glass thermometer. We can also use alcohol, pentane or other organic liquids for this purpose. So it actually depends upon the expansion with relation to change in temperature. Then we can have pressure gauge thermometers. Over here, what happens is that whenever the temperature rises, then we have some liquid or vapor whose pressure actually changes. Okay, so for example, we may, if it is a liquid, when you heat, okay, the liquid, if it is expanding, so we have a kind of a setup in which the expanding liquid or the vapors that are getting excited as the heat rises or the temperature rises, they exert a pressure on the surface, and that pressure is actually measured with the help of a pressure gauge. So over here, the change in temperature is actually calibrated with the pressure. Okay, so in the earlier one, we were just seeing how much the mercury has expanded in that column. We were just measuring the calibrating that height of expansion with the temperature. But over here, the rising liquid or the expanding liquid or the expanding vapors with the change in temperature, they actually exert some pressure on a surface, and that pressure is actually measured. So the calibration is actually done from in the terms of change in temperature and pressure. Okay. Then we can have differential expansion thermometers. Here, basically the thermometer is made up of a bimetallic strip. That means two different metals having different thermal expansion coefficients. That means the tendency of the metal to expand when heated is actually different for both the metals that you are using over here. So as the temperature will rise, one of the metals actually expands more than the other. It's resulting in a change in shape of the bimetallic strip. It might get bent towards one side. Right, so that change in shape or the expansion that is taking place is actually calibrated with the change in temperature. So in this case, the output due to differential expansion of two dissimilar metals produced by the temperature. If two strips of metals with different thermal expansion coefficients at the same temperature are bonded together, a temperature change can cause a differential expansion. So differential expansion means not equal. The expansion that is taking place in the two metallic strips is actually not equal. One strip expands more than the other. That results in a change of shape. Then we can have electrical resistance thermometers. Electrical over here, as the temperature changes, the resistance changes of the device, and then from that device, when clubbed with an electronic circuit, can actually give you a change in the resistance, and that indirectly gives you the change in temperature. Then we have thermocouples. Thermocouple over here, the temperature change is actually indicated by the production of voltage. You must we have discussed already that whenever there is a change in temperature, that is the two junctions, they are at different temperatures, a voltage is produced. Then you can have pyrometers or optical pyrometers. Over here, basically, we try to find out the temperature by matching the brightness of the source object with some known brightness object that is placed in the pyrometer. So pyrometer is actually a device in which, already there is a filament which is enlightened, and that light of that filament actually is controlled by some electronic circuit, right? So when you actually place your sample, now whenever the temperature is rising, we also see that the heated object also actually radiates certain visible light. Okay, so over here what we do is the brightness of the source we try to match with the brightness of the filament already present with us. Okay, so when the brightness of the two is equal, then जो हमारा source है उसका जो temperature हमें check करना होगा. Basically pyrometer के अंदर एक you can see in this figure that inside the pyrometer, the reference temperature lamp, as you can see right in the center, this is actually controlled with a electronic circuit, right? So what we try to do is we match the brightness of this reference temperature to the temperature source. एक object है आपके पास which is actually a source of temperature, उसकी अपनी कुछ brightness होगी, और एक रेफरेंस टेम्परेचर फिलामेंट लगा हुआ है पायरोमीटर के अंदर, उसकी कुछ ब्राइटनेस है जो कि आपके हाथ में है. ओके, सो वी ट्राई टू मॉडिफाई द brightness of this reference temperature and to a certain limit such that the two brightness become the same. Okay, so when the two brightnesses become the same, we actually try to find out with the help of this electronic circuit that what amount of current we had supplied to actually maintain that brightness. Okay, so with the help of that, we actually make certain calibrations, and then the temperature measurement is made with the help of that brightness. So this is one kind of way of measuring the temperature. Then thermocouple, obviously, this is one of the very popular devices that we are using for temperature measurement. And to a certain extent, most of you must be familiar with this. What basically thermocouple is that you make a circuit by connecting two dissimilar metals. Okay, and you have the junction at 2 points. Whenever there is a temperature difference between the two junctions, a voltage will be produced at the in this closed circuit. Okay, so if one junction is kept at a reference point, suppose 0, so usually what we do is we keep one reference point in a intact in an ice box or something, so that that reference temperature actually doesn't change. Okay, so and the other junction is actually the measuring junction, and whenever some certain temperature is subjected to this junction, since there is a change in the temperature in the two junctions, there is some temperature gradient develops, and that helps in developing a voltage in this closed loop that is formed. And in between, as you can see in the figure, you can actually put a voltmeter and measure how much voltage is produced. Okay, and then with the help of this equation, you can actually find out that what is the change in temperature. So in this equation, alpha, beta, they are constants depending upon the material that you're using. And usually, since alpha is a very large value in comparison to beta, so the square term can actually be neglected, and in the popular thermocouples we can use only the first term, that is E. The voltage that is produced is alpha into the difference in temperature. So from here you can actually, if you know the reference temperature, if you have kept it to 0 or something, some standard value, you can measure E. Alpha is a constant value, and you can find out the temperature T of the measuring junction. Right, so that is the basic principle of operation of a thermocouple. These are certain EMF curves. This is basically for different combinations of metallic strips or metallic wires, how the EMF changes with respect to temperature. So this graph is just for knowledge. You can this is useful while selecting the metallic strips for depending upon what range of temperature actually you want to work upon. Okay, so if you want a very high range, so you have to see from this curve that whether your the range of operation that you're working upon is suitable or not. Okay, so this just for different kinds of combinations of metals, it is showing you that how the temperature is, how the voltage actually is generated with the change in temperature, right? So these are some of the details of various types. These types that you see over here is nothing but the names are designated depending upon what kind of combination is used, under what temperature ranges they can be used, right? So this is now the extreme left, you see that the most linear range and sensitivity in that range. So most linear range is actually useful because then you try to actually operate your thermocouple in that linear range, because as we had studied earlier also, that it is always better to have a linear relation between input and output in your measuring devices. So this most linear range actually tells you that within this particular range of temperature, you don't need any extra calibration or any extra adjustment, mathematical adjustment. It will simply give you a linear relation between input and output. Okay, so this is just a summary of information about various types of thermocouples that are popularly used for measurement of temperature. Then certain laws are there. We have three laws which are pertinent to the thermocouples. The first one says law of intermediate metals. So the law of intermediate metals states that a third metal may be inserted into a thermocouple system without actually affecting the EMF generated, if and only if the junction with the third metals are kept at the same temperature. So suppose you have two metal wires A and B. Okay, so you have two junctions over there. Somewhere in between, if you want to insert a metal C, then the overall working or the EMF that is produced over here is not affected as long as the two junctions that you have newly introduced, they are at the same temperature. Okay, so in the figure you can see we have tapped the wire B and we have inserted another metal C in between. So if the two junctions of metal where the metal B and C are joined together, if these two junctions they are at the same temperature, then the overall EMF of the thermocouple actually is not affected. Okay, so third metal can be inserted in between provided the two junction temperatures are the same. Okay, and that does not affect the voltage that is produced in the overall thermocouple. Then law of homogeneous material, this law states that a thermocouple circuit that is made with a homogeneous wire cannot generate an EMF even if at different temperature and thicknesses throughout. In other words, a thermocouple must be made from at least two different materials in order to generate a voltage. Now this is very important point, that if you think that you can simply change the thickness of the wire and then you can use to make a thermocouple, no. If it is a homogeneous material, that is if the two metals are same, then there will not be any voltage produced at the junctions with the change in temperature. Okay, so it is very, very important that a thermocouple has to be made up with the metals of two different materials. Okay, two different metals have to be selected. Only then when with the help of temperature change, there will be a voltage generated. So that's the law of homogeneous material. You cannot use the same metal for both the wires. Okay, even though you can, if you think that you can change the thickness or something, it actually does not matter. Homogeneity is not to be maintained over here. Then we have law of intermediate temperatures. So over here, what it states is that if a thermocouple circuit develops a net EMF 1,2 for measuring junction temperatures T1 and T2, and a net EMF 2,3 for temperatures T2 and T3, then it will develop a net voltage of 1 and 1,3, that is the addition of two EMFs when the junctions are at temperature T1 and T3. So that's a simple thing. You have one thermocouple in which the junction temperatures are T1 and T2, and you have some voltage, suppose V2 generated. Okay, and then you have another thermocouple which has temperature T2 and T3, and you have some voltage V1 developed. So the law of intermediate temperature says if you use a third thermocouple, right, where the temperatures differences are T1 and T3, then the voltage V3 that will be produced over here will be the sum of the two thermocouples. That is, V3 will actually be V1 plus V2. Okay, so that is intermediate temperatures. If it's like a series connection. So if you have series development of temperatures, you can actually replace it with one thermocouple having, T1 and T3, and the voltage that will be produced will be the addition of the two voltages. Then another device that is commonly used for temperature measurement is the RTD or the resistance temperature devices. These are very high precision temperature sensors. These are more accurate in comparison to thermocouple elements. They maintain the accuracy over a longer period of time. Their range is very high. Okay, this could be either wire wound or thin film type. Now, RTDs basically they are devices where the resistance changes as the temperature changes. Okay, so as the temperature rises, the resistance also increases of these devices. These are special devices where the resistance also increases as the temperature increases. Okay, so the controller measures the resistance value and then converts it to temperature reading, fairly having a linear relationship. These are special type of resistances. They show a linear relation between temperature and resistance. Okay, so as the temperature changes, the resistance will be changed. Okay, but and unlike thermocouples, there is no new electrical circuit generated over here. It is just like a resistance whose value is changing. So what we have to do is every time we have to pass the current through it, and with the help of the formula V is equal to IR, we have to see that what is the present value of resistance. Okay, so basically it is put into a circuit, and when it is subjected to temperature, the effective resistance of this device changes. So when it is put in a circuit, there is some flow of current, and with the help of that, you have to every time you have to find out what is the value of this resistance. And that resistance, since it is linearly related to temperature, the reading is actually calibrated in terms of change in temperature. Okay, so the controller actually measures the resistance value and converts to temperature reading, the fairly linear relationship. Unlike thermocouple, there is no electrical signal generated, and the controller measures the resistance by passing current through the RTD. You can see in the figure that a somewhat linear relationship you have between temperature and the resistance. So this is a governing equation that we use for the variation of temperature. Again, over here, the second order and the higher terms, they are usually neglected. So we popularly use the formula R is equal to R naught into 1 plus alpha 1 into delta T. So over here, delta T becomes R naught is the resistance at 0 degrees temperature. Alpha is actually the temperature coefficient of that material of which the RTD is made, and delta T is actually the gradient of temperature, or you can say the change in temperature, and then you can find out what is the value of R. There is a new resistance that is generated. So the resistance of a conductor changes when the temperature is changed. The variation of the resistance R with change in temperature delta T can be expressed with the help of this formula. These usually the second order or the second power and onwards, they are neglected. So the formula that we use over here is R is equal to R naught into 1 plus alpha into delta T, where R naught is the resistance at temperature 0 degrees, alpha is the temperature coefficient, and delta T is the temperature change. So the change in resistance of the material per unit change in temperature should be very large. These are the requirements for conductor to be an RTD. Okay, so the change in resistance per unit change in temperature should be very large. This is basically indicating towards sensitivity. That is, it should have a high sensitivity towards change in temperature. For even a small change in temperature, there should be a large change in resistance. So that helps in making the measurability more suitable. Okay, so the material should have high value of resistivity. The resistance of material should have a continuous and stable relationship with temperature. And most common RTDs are made up of nickel, platinum, nickel alloys, etc. right? So these are the basic points that are required for any conductor to be an RTD. Okay, again, these are certain specifications of the metals, like resistance, temperature coefficient per degree Celsius, the range in which they operate, the melting point. Now over here, melting point of course is very important because you are subjecting a metal resistance to a very high temperature. So the melting point actually should be even more higher. Otherwise, the working of the resistance will not be proper. You know, you as you subject it to a higher temperature, if the material starts melting, then it does not work properly as a resistance. So these particular RTDs, they are made up of such metals which have a very, very high melting point. Then we are going to talk about the temperature sensor IC. Now LM35 is actually a very popular IC that is available in the market that you are using in your DIY projects also. In-house projects that you make, you can use this as a temperature sensor. This is actually an analog sensor. So LM35 is an IC, analog temperature sensor, whose electrical output is proportional to degree centigrade. Okay, LM35 sensor does not require any external calibration or trimming to provide typical accuracies. So this is one IC that is made very popularly used. It's a temperature sensor in which directly when it is subjected to the temperature, when it is subjected to any change in temperature, the electrical output or the electrical signal that it gives as an output is actually directly proportional to the degrees Celsius centigrade. So directly the the voltage that it is giving you is proportional to the temperature that it is measuring. So the output, you can see it's a 3-pin device. Okay, on one you give the input 4 to 20 volts. Then you have the second is the output pin, and third one is the ground pin. Okay, so the output that it will give you will directly be in terms of temperature. Okay, the IC is actually formed in such a way that it measures the change in temperature, and the internal circuitry actually generates an electrical output or a voltage output which is proportional to the temperature change, and the output that it will show you will automatically be in terms of degree Celsius. Okay, so you actually don't need to have any external calibration circuit or any other circuit attached to it for having any accuracy. It's a very accurate sensor, very popularly used sensor, because it's very simple to use. You do need not use any external circuitries along with this. You can simply use this 3-pin device for measuring the temperature and getting a proportional output value. So what is the basis of this? Actually, the NPN transistors are actually used inside the IC circuit. Okay, the base emitter voltage of a silicon NPN transistor actually has a dependence on the temperature over a small range of temperatures. Okay, so the base emitter voltage actually, for any transistor is actually temperature dependent in a certain range. So the same fundamental we are using. Inside this, we have actually 2 transistors. Okay, and the difference of the base emitter voltage is operated, at different current densities, and that fundamental is actually used to measure the temperature. Okay, so the base emitter voltage of a silicon NPN transistor has such a temperature dependence over small ranges of temperature. The difference in the base emitter voltage of 2 transistors operated at different current densities is used as a measure of temperature. Okay, when 2 transistors Q1 and Q2 are operated at different emitter current densities, the difference in their base emitter voltages is given by delta VBE is equal to base emitter voltage 1 minus base emitter voltage 2 minus KT by Q log of JE1 upon JE2. Okay, so where K is your Boltzmann constant, Q is the charge of electron, T over here is the absolute temperature in degree Kelvin, and J1 and J2 are the current densities of the 2 transistors. Okay, so somewhat this is just a rough figure how the transistors are used inside it. And over here, if I1 and I2, that is the current, if you maintain constant, then delta VBE is actually a linear function of temperature. In the earlier this thing, you can see the current densities, if I maintain this constant, okay, so the log term will actually get eliminated, and you get it becomes constant, and so you actually get a relation between the voltage and temperature, okay, because other things are constant over here. So temperature is a variable thing, and then resultant to that temperature, the change in voltage is actually a variable factor. Okay, so this is where the linearity in the delta VBE with temperature is good enough that most of the today's monolithic temperature sensor are based upon this principle. So NPN transistors, they have the base emitter voltage, and that base emitter voltage is actually dependent on temperature. Okay, so we in these circuits ICs, we are using two different transistors in such a way that the difference in the base emitter voltage of these two transistors is dependent upon the temperature and the current densities, log of current density. So if you maintain the current densities constant, you get a linear relation between the change in the base emitter voltage and temperature. Okay, so this is internally, all the calibration and all this mathematics is actually done internally itself, and at the final output you are getting a proportional value. Directly you are getting the value in terms of degrees Celsius. Okay, so internally it is actually measuring the temperature. That temperature is actually changing the base emitter voltages of the transistors that are connected. Those transistors that they are producing a, a proportional change in voltage, net voltage, and that net voltage is actually again represented on your console in terms of degrees Celsius. So finally, the answer that you are getting is in terms of temperature only. Internally, actually, there is a voltage being produced which is directly proportional to the temperature that it is being measured. Okay, so this is actually a very, very popular IC, and you can very easily use it for your projects, etc., that you work on. Okay, so this was some of the common methods with the help of which you can actually measure the temperatures, that is thermocouples, RTDs, and different kinds of thermometers. And this was one of the sensors that is very popularly used. So that was all about the measurement of temperature. In the next lecture we will be continuing this, talking about the measurement of speed and vibration. Okay, so that's it for today.